Like question B, I'm sorry, question 3 part B. Question 5 part B, I am giving extra credit for. This is something that I think you're going to be really good at by the end of the chapter. I will point out this is a proportion. I don't really want us to talk about it like a proportion just because there's some accidents, mistakes that can happen. So I'm going to show you a technique for dealing with that is, I think you'll find it pretty useful, and it works anytime you've got fractions. You could have multiple terms across both sides and it'll still get rid of those fractions. But let's go ahead and start with A. So on A, I'm going to go ahead and write this as, I'm going to distribute this negative 4 first. So this is going to give me a negative 2x plus 5. And then I have minus 4x, and then very carefully I write plus 8, right? Because I am multiplying negative 4 times negative 2, which gives me a positive 8 there. And then I have that equals 11. Negative 2x and negative 4x is negative 6 times x, plus 13 is 11. If I take away 13 from both sides, I do get that negative 6 times x is negative 2. 11 minus 13 is negative 2. And then I'm going to divide both sides by 6, or negative 6 rather. So I get that x is negative 2 over negative 6, which there is a 1 there, right? In fact, both of those are divisible by negative 2, so which is 1/3. So the value of x that makes this true is 1/3. And probably a good idea to grab that and run it through a calculator just to check. We'll be talking more about checking as we proceed through chapter 3 and 4, but for right now I'm just going to go ahead and leave this and say that x is equal to 1/3. But a really good thing to be able to do is just to verify that you have the correct answer. So we need to work on those skills. And then, the thing that's tough is if for some reason we're wrong, going through and correcting the problem, that's where it takes really a good trained eyes and a lot of practice to kind of identify where we make mistakes. I know it's hard for me to admit when I make a mistake. I do. I make a lot of mistakes. Just ask my sons or my daughter or even my wife. But I make mistakes, and then identifying them is kind of difficult. But training yourself to do that mathematically is pretty powerful. So let's talk about B. B was 2x plus 1 over 4, and that equals x over 7. So this technique you'll learn more about in the chapter, but I'm just going to kind of preview it here. If I know that if I have equal things and I multiply by equal things, I get equal things. Equal things times equal things equal things, right? So I could multiply both sides of this by the number 7. And I'm going to do that, multiply both sides by the number 7. So I'm not changing this equation, I'm just changing its form. It's still going to produce all the same x values. So equal things times equal things gives you an equivalent or equal equation. What's nice about this is over on the right hand side, I just created this giant 1, right? There's a 7 over 7. So over on that side now, I just have an x. Over on the left-hand side, I do have something a little bit more complicated, right? I need to multiply 7 times the quantity of 2x plus 1. So 7 times the quantity of 2x plus 1. And this is still all over 4. Now, I'm just going to lather, rinse, repeat, right? I'm washing my hands. I'm going to do this again, but this time I'm going to multiply both sides by 4. And the reason why I'm selecting the number 4 here is because this will produce a giant 1 with the 4 there, right? Because it's all multiplication. So when I do that, that 4 over 4 equals 1, and I'm left with this new equation now. I'm left with 7 times 2x plus 1 equals 4 times x. Now, I love this. I love this equation. It's a great equation because there's no fractions, right? I can easily distribute this 7, rewrite it as 14x plus 7, and that's equal to 4x. I'm going to just so you can see this, because I see this happen sometimes and people they forget that there's two sides to the equation. I'm going to subtract 4x from both sides. When I subtract 4x from the left hand side, that gives me 10x plus 7, but remember there's still two sides. When I take 4x away from this side, it gives me 0, right? So now I'm going to subtract 7 from both sides, so 10x is negative 7, and then to solve for x, I'm just going to divide both sides by 10. So x is equal to negative 7 over 10, negative 7 tenths. And again, we need to talk about how do we check those efficiently, how do we check that our answers are correct. But for now, I'm not going to show a check. I'm just going to go ahead and write down my solution. Oops. X is negative 7 tenths. Great. Let's go to the next page. Next page has some problems that involve simplifying things that are written in scientific notation. So there's two values here. The first one is 15,200. I know that to be in scientific notation, my decimal point would have to be here. Oops, not 2, 552. There we go. Now the question is, how many factors of x do I have to multiply the 1.52 by in order for it to become this number again, right? So if I'm sitting here and I'm just looking at, let me get a really thin pencil. That's great. I'm right here. Right? If I multiply by 10, it puts it here. That's 1 10, 2 10s, 3 10s, 4 10s. So I'm going to need to multiply this by 4 factors of 10, right? Or 10 to the 4th power. So my answer for A is 1.52 times 10 to the 4th. 1.52 times 10 raised to the 4th power. The next question, same thing. I know that my decimal has to be at the 1.5. It has to be at 5.3, right? So a number written in scientific notation always has a leading digit between 1 and 9. It could be a 1, 2, 3, 4, 5, 6, 7, 8, or 9, and then the decimal point has to follow it. And then I'm going to have to, in this case, divide by a bunch of tens, right? Because you can see this number 5.3 is way too large. I need to make it much, much smaller. So I've placed it here. Well, I don't like that pen. Let me get this thin pen. I placed it here, and in order to get it back to where it starts, I need to divide by 10. In fact, I need to divide by 10 1, 2, 3, 4, 5, 6, 7 times. And dividing by 10, I could do dividing by 10 7 times. I could do that, right? This is the one time when we really want negative exponents. So division by 10 is the same thing as multiplying by 10 to the negative 7th power, right? So just kind of a big idea. If you want to divide by 10, that's the same, right? That's 1 divided by 10. That's the same thing as taking and multiplying by 10 to the negative 1 power. Oh, that's wonderful. That's so cool. Maybe not. Let's write our answer down. So 5.3 times 10 to the negative 7th. Way over here, 5.3 times 10 raised to the negative 7th power. Great. Let's move on to 7. Question 7, we're asked to evaluate 4 different expressions, and I'm giving you a value for A, B, and C. And again, I want to caution you, remember A is negative 3, right? So when I set out to square this, because I can see this happening in the first problem, remember what's getting squared is the negative 3. So I'm very careful here to write down that negative 3 is getting squared, and then I'm adding 11 times C, and C I think is just the number 10, right? Well, negative 3 times negative 3 is positive 9. And 11 times 10 is 110. So we're looking at 119 here. So let's write that down. That's A is 119. And that felt relatively painless. Let's go over to part B. Again, A is negative 3. So I've got a negative 3. And then I'm subtracting B, and B is positive, but I'm subtracting it, so it's going to be negative 4, and I'm going to square that. So if I just simplify that part, notice it's negative 7 squared, and we saw this on a previous question. That's 49, right? Negative 7 times negative 7 is 49. Plus a 1, right? Plus a 1, and then plus 5 times C. Well, C is 10. 5 times 10 is 50. So this is looking quite nice. This is the number 50 plus another 50. That means that this is the number 100. Fabulous. Let's move on to part C. Again, I'm using the values. You can see them if you've got a copy of this downloaded, but A again was -3, so I've got my -3 plus C, which was 10. I'm subtracting 4 times A, and again A was -3, and then I've got plus 2 times B, which is the number 4. So -3 and 10 is +7, and then I'm going to have plus 12, right? 4 times -4 times -3 is plus 12, and then plus the number 8. So these are easy for me to add together. That's 20. So I've got 7 plus 20, which looks like 27. So I don't feel like I need a calculator with these problems. The numbers are nice. These are friendly without a calculator, these problems. Okay, let's look at the last one, D. On D, I've got 4 times B. I'm sorry, 2 times B. 2 times B. B is the number 4, so I've got 2 times 4 plus C, which was 10, and then plus 2. So that's the numerator. And my denominator, A, is -3, and I am subtracting from that 2. So let's rewrite the numerator. It's 8. Right? 2 times 4 is 8, 9, 10. And 10 plus 10 is 20. That's fabulous. That's a 20 in my numerator. And my denominator is -5. Well, 20 divided by -5 is just plain old -4. So there we go. All right, question 8. A typical bag of Skittles. Yes, I spend a lot of time at Safeway counting these. No, I actually looked this up. Apparently, a typical bag of Skittles has about 54 Skittles in it. Richard is eating 15 Skittles per day, and we want to convert this rate of Skittles consumption into bags of Skittles per year. Okay, so let's start with the one that we have, right? The one that we have is we've got 15 Skittles, Skittles, per 1 day, and we're going to convert this into Skittles per year. Well, one of the first things we can do, right? I know that I want to end up with years, but more importantly, I want to get rid of the days. So there is a relationship I know for days and years, right? There are about 365 days in one year. So this is the number 1, right? 365 is equivalent to 1 year, roughly, right? There is the leap year thing, but 365 days is equivalent to a year. What's nice about that is this has a 1 now that can be eliminated, right? The units day divided by the unit day, that unit goes away even though the numerical values stay. So what I'm looking at right now is the number of individual Skittles per year, right? The number of individual Skittles per year. I want to turn that into bags of Skittles. So let's come back up to this fact. It says that a typical bag of Skittles contains 54 Skittles. So that sounds like a number 1 to me. And I can write it in any way that I want, right? I'm just going to write down that 1 bag of Skittles is the same thing as 54 individual little tiny Skittles, Skittles. So if a bag is 54 Skittles, this is fabulous because I want to cancel out Skittles from the problem that I have. So I don't even have to write the reciprocal. I'm going to bring this down exactly as I've written it. I'm just going to write down that 1 bag of Skittles, 1 bag of Skittles is the same as 54 individual Skittles. So there we go. Dimensional analysis now lets us point out the fact that our individual Skittles cancel, right? That forms a giant 1. And the only units we have left is bags, and remember these are bags of the Skittles per year, and that's exactly what we want. We want bags per year. So my numerator here, if this is just down to the arithmetic, the numerator is 15 times 365, and those are bags, over 54 years. Right, that's the only thing we're left with. Now let's do the arithmetic there, and I don't have a calculator. Oh geez, let's see. Wouldn't it be nice if I can quickly grab one? There it is. I'll just grab this calculator and go ahead and do 15 times 365, and then I'll hit equals. So that's 5,475, and I'm going to divide that by 54, and I get, I'm going to just round it to the nearest whole number of bags. So I get, this is about 101 bags. So if I consume just 15 little Skittles each day, that's the same as eating 101 of them in an entire year. So stock up.